My goal today is to prove the strong duality theorem for linear programming. I'll start by stating Farkas's lemma again. We proved like half of it last time, and now we'll prove the other half. So A is a real m by m matrix, and B is some real vector of length m. So I want to say that exactly, actually, just check something. So yeah, I want to say exactly one of the following two things hold. So exactly one of the following holds. So the first thing is that there exists some x in Rn where like a times x equals b, and the entries of x are non-negative. The second kind of alternative is that there could exist some y in Rm with y transpose times A non-negative and y transpose B negative. So okay, this one, y transpose A, what I mean is it's a non-negative vector, right? All the entries are non-negative. And then this y transpose B, yeah, that's just a number, right? Okay, so last time we showed they can't both hold. This time this time we'll show that they can't both be false. And I'm going to use this thing that I stated last time called the separating or hyperplane separation theorem, or maybe I'll call it separating hyperplane theorem or something. So if I've got a set C in Rn, so if C is non-empty, closed, and convex, and Y is not in C, so it's in Rn minus C. Okay, the idea here is I've got some closed convex set. I've got some point outside of the set. I want to say there's a hyperplane that separates them so that Y is on one side and C is on the other side. So then there exists some W in Rn and alpha, which is a real number, such that W transpose Y is positive, or sorry, not positive, bigger than alpha, which you should think of as like Y is on one side of some hyperplane, and W transpose X is less than alpha for all X in C, which is like the elements of C are on the other side of the hyperplane. If I have time at the end, I'll prove this separating hyperplane theorem. But for now, let's just assume this and then use it to prove Farkas's lemma. Okay. I never know how long these lectures are actually going to take. So yeah, if at the end, if we have time, then I'll do it. And if we don't, then I won't. So. Okay, so to prove Farkas's lemma, we already proved one half. So we already proved that 1 and 2 can't both be true last time. So they can't both hold. Okay, the proof was pretty easy. You just like write them down and then like multiply things on the left or the right side and make some observations and get a contradiction that something is negative and something is also positive, which is, yeah, it can't be true. Okay, so now we show that at least one of them is true. So okay. And then exactly one of them is true. Okay, so here's the, and somehow I want to use the separating hyperplane theorem. So I want to somehow construct some kind of a convex set where we can apply that theorem to it. Here's how I'm going to do that. So I'm going to let let A1 up to AN be the columns of A. Right, so A has M rows and N columns. So in other words, A looks like, A1, A2, up to AN. Okay. So here's the convex set that I'm going to be dealing with. I'm going to define C to be the set of all. Basically, I'm going to take all the ways of adding kind of a positive or non-negative combination of these columns. So C is just the set of all vectors I can get by taking some sum, let's say lambda, let's say the sum j equals 1 to n, lambda j aj, where lambda 1, lambda 2, dot, 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 up to lambda n are non-negative. Okay. Note that this is different than the convex hull. Like when you compute the convex hull of finitely many vectors, you would normally have like these lambdas being non-negative and adding up to 1. But we're not going to have that restriction. I'm just going to say take any non-negative combination of those column vectors. Okay. Yeah, in some sense, this is containing kind of the same information as that, because it's just, it's like many copies of that. It's like where they sum up to 1 or 2 or 3. Or it's like, yeah, you can scale it and unscale it. Yeah. Somehow, this is going to be useful at some point that we can, scale things up to infinity and get a contradiction at some point. So yeah, this is just kind of a convenient thing. By the way, this is for kind of terminology, this is something called the convex cone generated by the A1 up to AN. So if you ever hear somebody talking about convex cones, this is what they mean. It's like, it kind of looks like a cone, right? If I take a bunch of vectors and then I take, so their convex hull would look like this, but then if I take all the scalar multiples, it's gonna go off to infinity, right? And it kind of looks like a big, kind of a big cone, right? Okay. Now, I think it's fairly evident that C is closed and convex. Right? The fact that it's closed basically just, you can probably just derive from the fact that the set of all such lambda is closed, like the set of, you know, yeah. And then the fact that it's convex is, yeah, also fairly obvious. If I take two things in the set, then anything on the line segment between them should also be in the set, because, yeah, if you can express two things like this, then like, and then I take like some positive combination of them, then it's also going to be in the set. Okay, and this is important because we can apply our theorem to it. So okay, let's kind of break this into cases. So suppose that the vector B is in C. Note that, like, C is a subset of R to the M, right? Because all of these column vectors are of length M, and B is in R to the M. So like this kind of makes sense, right? It could be the case that B is in C or it's not in C. So I claim that if B is in C, then actually we're done. So I want to show that either 1 or 2 must hold. And can anyone see maybe which one's going to hold? Or even, maybe I should just get you guys to guess or vote on it or something. Yeah.
Isn't B in a different dimension space than C?
No, so C, like, so all of these columns, this matrix has M rows, so all of these columns are of length M. And C also has length M, yeah. Yeah. So N, oh, wait. Yeah, M by N, yeah. M rows, N columns. Yeah. So okay, if B is in C, the thing I'm going to be able to prove is true is the first condition. Because like basically the lambdas, so if B is in C, right, then there exists some lambda 1 up to lambda n with B being equal to the sum lambda j aj. If we kind of think of this, what this means in terms of matrix multiplication and stuff. Oh yeah, and these lambdas are all non-negative, right? Because, that's the definition. Like this is, I mean, really what's happening here is some kind of matrix multiplication. So what I'm going to do is I'm going to let x be the vector lambda 1 up to lambda n. So then definitely x is non-negative because the lambdas are non-negative. And if you think of what a times x is doing, it's basically doing the same thing as this, right? Because I'm taking, how does matrix multiplication work again? Like I take the first row of this times the first column of that, which this is just one column, so that's good. Take the first row of this times this, and it should give me the first coordinate of whatever the product is. And like that is like the first coordinate of B by this equation, right? So yeah, so this is, by this thing. Okay, if you think about it, yeah, this thing is doing the same thing as this matrix multiplication, so they're both going to give you B. Any questions about that? Okay, so then second case is that it's not in C. Maybe I'll erase this part. Okay, any guess what I'm going to like do with this information? Yeah, that thing. Yeah, use the theorem. Yeah, exactly. Okay, so C is closed and convex, so I can use the theorem. So there exists some vector W. Maybe it's slightly confusing that in the theorem, I'm using Rn and now I'm using Rm in this, but anyway, in our application of the theorem here, M is n, but not the n that's the number of columns. But anyway, yeah. Okay, so there's something like this and some alpha in the reals, such that what do I want? That W transpose B is bigger than alpha, and W transpose X is less than alpha for all X and C. Okay. So now we have to do a little bit of thinking. So observe that the zero vector is in C. Right? And that's just because I could let my lambdas be 0. All of the lambdas be 0, and I get the 0 vector. But now if we think about what if I let the 0 vector be x? Well, then this number is going to be 0. So I need alpha to be bigger than 0. Like alpha, so therefore alpha is bigger than 0. Otherwise, this wouldn't make sense. So W transpose times 0 is less than alpha, because that has to hold for everything in C. And so alpha is positive. But now actually we're going to get something interesting from this. So I claim that actually if I take anything in anything in C, that this dot product not only does it have to be less than alpha, but I claim it has to be at most 0. Okay? Because if this dot product, so if there exists X in C with W transpose X being positive, then I claim that this is just not possible, because this C is closed under taking positive scalar multiples. So if I just, so this is some positive number. If I replace X with 1,000 times X, it's also in C. Okay? And eventually, if I pick a big enough scalar multiple, positive scalar multiple, it's going to go above alpha. Right? So I need that this holds for everything in C. If anything was even positive, I would just scale that thing up so much that it's going to be bigger than alpha. Okay, so if there exists such an X, then if I take, let's say, 100 times alpha over W transpose X, so this is just a constant, times X, that's also in C. But this would violate the condition, this condition. So this violates the W transpose X less than alpha for all X in C. Right, so if it's positive even just a little bit, I could just scale it up, and I get a counterexample to this. Okay, so it must be the case that W transpose X is non-positive for all X in C. Does that make sense? Okay. In particular, each column vector of A is in C, because you could just take the lambda equal to 1. So maybe I will kind of so in particular, W transpose AJ is non-positive for all J because AJ is in C. Okay. So now what I'm going to do is I'm going to let the vector y be equal to negative W. So what I'm trying to drive at here is I want to show that the second condition is true. Right? And basically, so this thing I proved about W is going to translate to this statement about y, because I'm going to take y is now negative W. And that's going to be kind of useful for this, because if everything was negative before, if I take the negative, it's going to be anyway, it's going to be positive or non-negative, I should say. And then I'm going to want this to hold as well. So yeah, then y transpose times A is just the same thing as negative W transpose times A, which, yeah, if you think about it, this thing I said about the columns here is going to show that that's non-negative. Yeah, because this is just computing, this is a row vector. I'm just multiplying by each column vector, and like all of those things are non-negative. And if I take y transpose B, that's the same as negative W transpose B, which over here I showed is, kind of by construction, this is less than negative alpha because of that, which is less than or equal to 0. Or it's even less than 0 because alpha is positive, which we proved over here. So condition 2 holds. Okay, so that completes the proof. So yeah, in case 1, you get that condition 1 holds. Case 2, you get condition 2 holds. Yeah. Any questions about that? It's a lot of just like matrix multiplication, and like you have to think about, okay, what's rows and columns and keep all of that straight. But yeah, it's none of the steps are like hard, but I think it's kind of clever actually to come up with that. Okay. So now what I'd like to do is, I'm not actually going to use Farkas's lemma as it's stated here to prove the strong duality theorem. I'm going to use a slightly different version of it, but I'll kind of briefly say why they're the same thing, or at least why this one implies the other one. So this one's called, I don't know, people have different names for everything. Maybe some people will call this one, like they'll say it's some kind of version of Farkas's lemma, which it basically is. I've seen it sometimes called the theorem of the alternative or something. So let's just call it that. I don't know. Okay, so this has got the same kind of setup as before. A is a m by n matrix. B is a length m vector. And it says kind of similarly exactly 1 of the following hold. So this time, our first condition is, so yeah, these conditions are going to be a little bit different. There exists some x in Rn with a times x at most b. Okay. So I've got I've got a inequality instead of an equality, and I'm now going to drop this condition that x is at least 0. Or the second alternative is that there exists some y in Rm. Now this one's going to be an equality, A transpose y equals 0, so equals the 0 vector. B transpose y is negative. Oh, this, before I was writing this, but it's the same as this, right? And y is non-negative. Okay. Basically, the proof, at least the proof idea, is as follows. Just apply Farkas's lemma with a slightly different matrix. So let's say A prime be the matrix where I take A, negative A, and then let's say IM. So IM, I mean the M by M identity matrix. And then apply this Farkas lemma. There's then a little bit that you need to think about, but yeah, it turns out, so I mean, if you apply a Farkas to this thing, if you're in this alternative, it ends up translating. You can come up with some x that satisfies this, and then if you're in this alternative, you can come up with a y that satisfies this, and vice versa. It's it's kind of equivalent. Yeah. Essentially, this thing kind of, remember we did this thing with slack variables last time? Essentially, this identity matrix here gives you some slack variables. This A and this negative A kind of turn this, the slack variables basically turn this equality into this A and this minus A basically cause this to be equal to 0 instead of greater than or equal to 0. Like there's just some stuff going on here, but it's not too complicated. If we have time, I could go through that more properly. But basically, I want to use this to prove the strong duality theorem. Okay, so this is what I'm going to assume. So yeah, that there's exactly one of these is always true. Okay. So let's recall what the strong duality theorem says. So for any primal linear program in standard inequality form, if the primal and the dual are both feasible, then the value, meaning the actual optimum for the primal, is equal to the value of the dual. Okay. So it's called strong duality because we've got this equal, right? Maybe I should remind you guys what the primal and the dual are. So here, like the primal linear program is maximize C transpose X subject to AX less than or equal to B and X at least 0. And then the dual is minimize B transpose Y subject to A transpose Y at least C and Y at least 0. Okay. So in the weak duality theorem, we already proved one direction. So by weak duality, we already know that the primal is less than or equal to the value of the dual. So we need to show the other direction. Okay. So if you think about it, like the primal is a maximization problem and the dual is a minimization problem. So actually all I need to do is find an X where, okay, the constraints have to be satisfied, and C transpose X, I want to make if I can make C transpose X bigger than B transpose Y for just one choice of X and Y, then since this is a maximization problem, the maximum will be even bigger than that. And since this is a minimization problem, the minimum will be even smaller, potentially. So we just need to find one X and one Y. So I'll just say, so it suffices to find a primal feasible X and dual feasible Y such that C transpose X is at least B transpose Y. Because if there's even one solution to this, then yeah, the maximum would be even bigger, and the minimum would be even smaller. So that would prove that the primal value is bigger, at least as large as the dual, right? Okay. So this is our goal, find an X and a Y with those properties. Which actually just, it just kind of boils down to solving a system of linear inequalities, right? Because to say that X is primal feasible is just to say, oh, I want this system of inequalities to hold. To say Y is dual feasible, I just want these inequalities to hold. And then I have one more inequality, which is this one, and I want that to hold. So I have this big long system of inequalities, and I just want that to hold, where I've got the number of variables I have is n plus m. So I've got the variables of x and the variables of y. I just want all of these things to be satisfied. So in other words, okay, so in other words, we want to choose, we've got kind of n plus m variables, y1 up to, sorry, x1 up to xn, and y1 up to ym, such that ax is at most b, x is non-negative, a transpose y is at least c, y is non-negative, and then we want this to hold. So c transpose x, we want to be at least b transpose y. Okay. Now let's just convert this into a single linear system of linear inequalities where all the inequalities go the same way, because then it'll look like a sort of standard kind of linear programming, or like a polyhedron thing or something, right? So this is the same as saying ax is at most b, negative x is at most 0, negative a transpose y is at most negative c, negative y is at most 0, and actually, sorry, it's going to be convenient to do these in a different order. Sorry. I'll do ax at most b. Apologies for that. A transpose y at most negative c. It's just going to be nice to have everything organized in a good way. Negative c transpose x plus b transpose y at most 0. I think that's the same as this. Yeah. Negative x at most 0, negative y at most 0. Okay. So this is like our only goal now. Just find these x's and y's, right? And then we'll be done. Okay. I want to apply this theorem of the alternative to this, but I need a matrix and stuff. So let's figure out what that is. And basically, all I'm going to do to come up with a matrix and a vector is to kind of just incorporate all of this stuff into one kind of matrix inequality, which I can do by just saying, okay, I'm going to let M be the matrix. So I can explain what it is in words, but it's probably better to draw a picture. So in the top kind of left corner, I'm going to put the matrix A. So it has M rows, N columns. Okay. I'm then going to put zeros here. Okay, so this is going to be a 2n plus 2m plus 1 by n plus m matrix. These numbers are kind of natural because if you think about how many constraints and how many variables you have here, you have n plus m variables. So that's the number of columns. You have m constraints, n constraints, one constraint, n constraints, m constraints. So it'll all add up to that. So now here I want to put negative A transpose. And here zeros. And that'll be n things. So I'm just going through all of the things here one by one, right? Here I've got negative C transpose. So this is just one row. And here I'm going to put B. And here I'm going to put in an n plus m by n plus m identity matrix, but with, well, with negative ones instead. Yeah, you're right. Yeah, B is like a column vector. Thanks. Okay. And now I also want a vector to correspond to like the right-hand sides of these inequalities. So let's do that too. So, so M is this matrix, and D is this vector, where I'm going to take my first M rows. So this is just, yeah, it's just a vector, so it's skinny. This is B. Then I've got minus C, so that's length M, length N. Then I've got a 0, just 1 0. Then I've got a bunch of other zeros. So I've got N plus N more zeros. So yeah, that's like B and C and 0, and then a bunch more zeros. Okay. So yeah, it's, I guess I'm just kind of there's no good reason. I could have just said n plus m of them, or sorry, n plus m plus 1. I guess I'm just separating it out to say, just to say that like, I guess I should have, if I was separating that one out, I should have said there's like also n and then m. Just kind of separating out into like this constraint, that constraint, that's just 1 0. This is like n zeros, and that's m zeros. Okay. So now I go back to my theorem of the alternative. And in one case, I'm happy. So let's apply that with, instead of A and B in the theorem, apply it with M and D. Well, I want to claim I'm happy in both cases. We have to deal with both of them, but there's one case that's like particularly good. Can you see which one? It's a bit awkward because my x over there doesn't mean the same thing as x over here, and A is now M, and B is now D. But yeah, does anyone, I guess since I said x, I'm kind of giving you a hint, it's the first one. Because yeah, in the first case, so So yeah, by the theorem of the alternative, either the first case holds or the second case holds. So, so let's say theorem, I don't know. Yeah, okay. Well, let's just say, so if there exists, let's say some z in R n plus m, such that mz is at most d, well then I just take my first n entries of z, I call that x. I take my last m entries of z, I call that y. And x and y will satisfy all of these constraints. So then I get my x and y. So this is, the x comes from the first n coordinates of z. And y is the last m coordinates of z. Right, because yeah, if you kind of reason out what this is saying, this yeah, it will give you the right thing. Okay. So yeah, in the first alternative, I win. So because I find the x and y that I need. So we assume that the that doesn't occur, which means that the second alternative occurs. Okay. So by the theorem of the alternative, if no such z exists, okay, then there exists, well, there exists like a y, like the second condition. I'm not going to call it y because like I'm using y for something else in this proof already, but let's call it w. So then there exists a w in r to the 2n plus 2m plus 1, because that's the number of constraints we have in this matrix, such that m transpose w equals 0, d transpose, because remember the d, the b over there is the d over here. D transpose w is negative, and w is non-negative. Okay. Does that make sense? Okay. So let's figure out what does all of this stuff mean. So let's say that we can kind of split off all of these different entries of w. Let's kind of split that into separate vectors and kind of think of them separately. So I'm going to think of w as like, so I take the first m entries, and I'll call that p. The next n entries I'll call q. And then I've got one entry, which I'll call r. All of these are corresponding to the different kind of blocks of this matrix, right? M, n, 1, and then like n, and then m. So, or sorry, m and then n. Am I doing this right? Well, we'll see. this is S. Yeah, okay. And it has length M, and then I've got T, which has length N. So if it's not clear, in this picture I'm defining P, Q, R, S, and T, right?
Negative x before negative y.
Yeah, maybe should have done that the other way around.
N and M for S and T.
Yeah, probably. Let's see.
Usually T is N and M.
Yeah, that probably does make sense. Let me just check what's going on here. I think you're right. So let's go with that, and then, yeah, I think you're probably right. So sorry, the length of S should be N, and the length of T should be M. What you're saying checks out, so, like, yeah, that seems most natural. Okay. So I want to interpret this information in terms of these vectors. So I claim that M transpose W being equal to 0, what this really means is two things. So I claim, so maybe I'll write it down and we can kind of think it through. So I'm going to say that this means that P transpose A minus R times C transpose minus S transpose is the 0 vector. And that negative Q transpose A transpose plus R times B transpose minus T transpose equals 0. Okay. So how is that working? If I take M transpose, a row of that, the first row of that is the first column of this. And then I multiply that to W, so it's like taking the first column of sorry, maybe what I mean here is it's going to be easier to see it if what I mean here is W transpose A is 0, or sorry, M is 0. It's the same thing, it's just taking transposes. Yeah. Is this making sense? I can't see all of this algebra from here. Yeah. So this like P transpose A is like taking the P vector, multiplying to this. Then I kind of multiply Q times a 0, doesn't show up. And then R times, the first so if I'm doing the first entry, then it's, R times the first entry of negative C. And then it's just giving me kind of a negative S, when I'm in sort of this part of it. The first, so I think this is, and then once I get sort of over here, it's giving me the second equality. Okay. Yeah. By the way, you're not going to be like asked to do this yourselves or something on like this is really complicated, but the point of this is really the statement of the theorem. Like the statement of the theorem is amazing, that the dual has the same value as the primal. What we're doing right now is just proving it, but after that, you really just want to know that the statement is true. Okay, let's interpret this D transpose W being negative. And this one's easier. I think it just means that B transpose P minus C transpose Q is negative. Okay. And I mean, for whatever reason, I wrote all of this in this form in the notes, but I kind of want to transpose all of this. I mean, this has, like this, so yeah, I'm going to change this to A transpose P, which is the same thing. You just take transpose, and then these transposes can go away. And similar here, I can just switch the order of the multiplication. And get rid of all the transposes. Okay. What I'm aiming for here is a contradiction. Because in the first alternative, I got what I wanted. In the second alternative, I want to derive nonsense. I want to derive a contradiction here because I liked what happened here. It gave me my x and y that proved the theorem. In this case, I want to get a contradiction. Okay, so for now on, all I'm going to deal with is, so it now no longer matters what this matrix was, and all I care about is this equality, and this inequality. Okay, so we're going to keep that, and I'm going to get a contradiction from it. So this can be erased. So there's one slightly awkward thing. At some point, I would like to divide by r, but r could be 0, so I need to treat that as a separate case. So let's kind of break it into cases that maybe r could be 0. Okay. So in this case, our things kind of are more simple. It's like A transpose P equals S, and A times Q, no transposes, equals T, right? Because the R is just 0. Okay. So this is the case. Actually, at this point, I haven't used the fact that, remember in the statement of the theorem, it says that the primal is feasible and the dual is feasible. I haven't used that. So this is where I'm going to use it. Yeah, I'm pulling it over to that side, and then I've got a negative t here and positive aq. Yeah. Okay, so let x be primal feasible and y be dual feasible. Okay. Okay, so here's something I want to observe. So let alpha be any non-negative number. And I'm going to look at A times x plus alpha q. Okay. So these are like this, the right, like x has length n, q has length n. I can do this, right? So this is A times x plus alpha A times q. And A times q is negative t. And x is dual feasible, right? So this is at most, primal feasible. So this is at most b. And this is alpha minus alpha t. And t is non-negative. The reason t is non-negative is because w was non-negative, and t is just like some part of w. So this is at most b. So from this I get that if I take x plus any positive constant or non-negative constant times q, it's going to be it's primal feasible, because so this inequality is because t is non-negative, which holds because w is non-negative. So therefore, x plus alpha q is feasible, for all alpha non-negative. Similarly, so it's like the exact same calculation. Y plus alpha p. So instead of taking x plus alpha q, I'm taking y plus alpha p is dual feasible. For all alpha. Yeah, non-negative. Yeah. If I have some negatives, it's going to screw it up. Yeah. Thanks. But I claim that this is going to be a contradiction. Okay. So by weak duality, so I'm actually going to use the weak duality theorem here as part of the proof of strong duality. So by weak duality, what weak duality really tells us is that for any primal feasible point, including, for example, x plus alpha q, if I take the objective function at any primal feasible point, it's at most the objective function of the dual evaluated at any dual feasible point. Because weak duality says that the value of the primal is at most the value of the dual. So this has to be less than or equal to that for all possible primal and dual feasible points. But if I rearrange this, this means that C transpose x minus B transpose y is less than or equal to alpha times B transpose P minus C transpose Q. Okay, so this is just bringing in the C and the B and putting all the things with alpha on the right side and putting the other things on the other side. But this holds for every single alpha. But also, this number here, we kind of deduced that that's negative. So this is It's right there. But this is not possible. I mean, this is a negative number. This is a number. It's just a number, which is less than every possible constant times every, like, any possible negative, or some. So this is just some negative number. This is some number. It could be negative or positive. I don't care. But alpha could be anything. So this cannot hold for all alpha, because this would be negative infinity. So, so this is, so since B transpose P minus C transpose Q is less than 0, and alpha is arbitrary, and also x and y are just two fixed, like I just picked any two feasible points, right? So this is a contradiction. Because basically you'd have to have this number being negative infinity. Okay. Does that make sense?
Did we assume anything, or is this just showing that R can't equal 0?
Yeah, so then we have to do the second case that if it's non-zero. But this is, yeah, so this is just for the 0 case. Yeah. I can't say that I have a lot of intuition about what's going on here. We're just kind of moving inequalities around and stuff, but yeah, it's kind of it's a fairly non-trivial proof. Okay, so if we're okay with that, then let's move on to the case where R is non-zero. This one's actually shorter. Okay, so now R is non-zero. Here's the thing, R is one of the entries of W, and W is non-negative, so R is positive. So yeah, so R is positive because, you know, W is non-negative, and like R is one of those entries. Okay. I claim that so R is just a number, right? So I can do like 1 over, and it's a non-zero number. So I claim that 1 over R times Q is primal feasible. Okay. So, okay, one thing, to be primal feasible, you need to be a non-negative vector, but it is, because it's part of W. So it is non-negative because W is non-negative. Now I just need to check A times that vector. But I've got this formula here for A times Q, actually. Oh, yeah, thanks. Yeah. So yeah, this is the same as by linearity 1 over R times AQ. And AQ is the same thing as R times B minus T. So this is 1 over R times B minus T, which is, yeah, B minus 1 over RT, which is at most B, because, again, T is non-negative. And then similarly, 1 over R times P is dual feasible. yeah, for that you just use this equation thing, right? Okay. Now we're going to use weak duality again. Because I've got, by weak duality, it should be the case that if I take a C transpose times some, any primal feasible point, like 1 over R times Q, that should be at most B transpose times any dual feasible point, like 1 over R times P. But the 1 over R's cancel. But this contradicts the thing over there again. I hope. Yeah, it does. This D transpose W negative meant that B transpose P minus C transpose Q is negative. So like this should be bigger than that one. But by weak duality, it's actually smaller. So this contradicts. So this is a contradiction. Because, yeah, this inequality contradicts that one. Okay. Any questions about that? Yeah, I don't have any deep intuition to share with you about this. But here's the thing. Now we've proven it. Now you can just use it. Whenever you have a linear program, if you've got the primal and you've got the dual, they have the same value. And that's kind of an amazing thing. And it's going to be applied to like many things that we do in this course.